Here we go. Good morning, ladies and gentlemen. This is an interesting session on C1 chemistry. My name is Jan de Boer, and my co-chair is John Armour. We are going to try to keep this thing going, and therefore I will introduce the keynote speaker of today, who is Simon Podkolzin. Podkolzin. And Simon is from the Stevens Institute of Technology. He got his degree in Russia at the State University of Oil and Gas, and then worked at UOP for a number of years, and then went to the University of Wisconsin-Madison to get his PhD. After that, he worked as a senior research engineer for Dow, and finally in 2009, he joined as a professor in chemical engineering the Stevens Institute of Technology. So, he's going to talk us today about the development of heterogeneous catalysts and catalytic processes for energy and chemical feedstock applications. Go ahead.
Well, good morning. Thank you for coming on Monday morning. So it's really tough after the nice reception we had last night with beer and wine. A special thanks for our international visitors, as you're probably still adjusting to a different time zone. So Monday morning is always tough. So please find the place in the audience. Thank you for coming. I'll be presenting joint work with Israel Wax. We'll be talking about the structure of molybdenum oxides and their regeneration in molybdenum ZSM5. And the reaction that we evaluated it for was methane conversion to benzene. In the introduction, they mentioned that I work at Stevens Institute. This is a very small university by American standards. We are located on the Hudson River, on the other side from Manhattan. So this is the university campus. And the reason why we're so small, only about 5,000 students, is because we don't have a place to grow. So this is it. We're constrained by the surroundings. This is the administrative building. We are at the highest point on the Hudson River. And we actually have a cannon located right here, which points toward Wall Street. So just in case, we can defend ourselves against bankers and lawyers from Wall Street. So we can focus on the science. The motivation for this work, there's a lot of natural gas in the world. Probably 30 to 60% of it is stranded. That means that we know exactly where it is, but it's just not economical to extract it because the shipping costs are too high. So if we can develop technologies for processing that natural gas into anything, into a liquid, into a solid, anything that we can ship, then we can unlock those resources. But that's really not the problem, because if we know where the gas is and we don't have the technologies how to extract it, we can just leave it there and live with something else. The problem is with the associated gas. So when people drill for oil at remote locations, there's associated gas that comes with it, and that associated gas, if it's not economical to transport it, then what we do with it is just vent or flare it, and this is really unacceptable. So in the world every year, about 150 billion metric tons are flared and vented, and this is a big environmental issue. And in addition, the amounts are so huge that this represents about a quarter of all the natural gas consumption in the US. So if we can stop this will be enormous. So there are multiple technologies that are evaluating for this, and this is too expensive to build a Fischer Tropsch plant at remote locations. So we need something alternative. We need something different that we can implement at remote locations. So one of the chemistries under development right now is direct methane conversion into aromatics. This is the main reaction. So this would be ideal for stranded gas because we don't need any other reactants. We can just take methane, produce benzene and other aromatics, and then we can ship them. So that would be perfect. We can use the hydrogen to power up the plant. We should be all set. We don't use any oxygen, so there's no risk of explosion, over-oxidation, so it looks perfect in principle. The challenges are the conversion is limited, and the catalyst deactivates rapidly. So we'll look at the catalyst regeneration, and we'll mostly focus on the structure of the catalytic active sites. What is the structure? That should be helpful in the development of the newly improved catalyst. So the topic we cover is the initial structure of molybdenum oxide, then what happens to the catalyst once we start reacting it with methane, and then the last one is the regeneration with gas-phase oxygen. Here we're comparing Raman spectra for just blank ZSM5 with nothing on it. So this is the hydrogen form of ZSM5. And then the catalyst with the 3-weight percent molybdenum. We have 3 new Raman bands. So what we will try to do is to find the answer is, what are they? So what are the molybdenum oxide species that give rise to those 3 new bands? The salt that we use to impregnate how we prepare the catalyst is molybdenum heptamolybdate. We have 7 molybdenum atoms in the salt, and then we dry and calcite it. This is a study that has been done by Israel Wax and published about 5 years ago. It determines the UV spectra of different molybdenum reference compounds. And what it plots is the average number of molybdenum-molybdenum bonds versus the edge energy from the UV spectrum. So if we look at different molybdenum compounds, so this for the molybdenum clusters, then for the molybdenum chains, then for dimers, and finally for isolated molybdenum species in the solution. So when there is just one molybdenum atom in the structure. We show a linear relationship, so then we can compare it to UV spectra from the molybdenum ZSM5. And that is the number. So we are well into the region of isolated molybdenum species. So based on the UV spectra, we think that the molybdenum species are atomically dispersed with just one molybdenum atom. So if we look where in the zeolite those molybdenum species can be located, the obvious anchoring sites are the aluminum framework positions. So if we have aluminum in the framework, so initially in the hydrogen form, the counter ion is H+. So before we put the molybdenum on it. Based on the UV spectra, we don't have any DD band transitions. That means that the chromium has to be in the +6 oxidation state. In addition, the catalyst is white. So if molybdenum is in any other oxidation state, we will have a color. So it is definitely +6. So if we need a structure with molybdenum in +6, and we want to put it on an anchoring site, replacing 2 hydrogen atoms, the structure has to be with 2 terminal oxygen atoms. So this is -2, -2, and 2 from the zeolite. Then we have our +6 for molybdenum. So this is the structure. It's on 2 framework aluminum atoms. So we called it a double aluminum framework site. It has 2 terminal oxygen atoms. These molybdenum oxygen bonds from the calculations are shorter, and then the bonds that to the oxygen atoms in the zeolite framework are longer. So this is single bonds. Where can it be silica? Molybdenum ZSM5 is a silica-rich zeolite. So there is no locations where the aluminum is another neighbor of aluminum. The second neighbors were ruled out by previous studies by NMR. So this is the first neighbor, this is the second neighbor. So the first neighbors are impossible. Second neighbors were ruled out, so it has to be a third neighbor. So what we did, there is a very long and ongoing debate about the location of aluminum in zeolites. So we try to stay away from that debate. So what we did, we just evaluated all possible sites in the zeolite. So everywhere where the aluminum can be a neighbor of another aluminum. So computationally, it's boring, but it's doable. So that's exactly what we did, and we found all the locations where the aluminum can be another neighbor of aluminum and serve as an anchoring site for molybdenum species, because it's basically a geometric constraint. So they cannot be too close, they cannot be too far. It has to be just right. And we found that it has to be only a third neighbor. And not just a third neighbor, but it has to be a special third neighbor. So we identify those locations. It can be in 6-member ring. So what the structure does, at first it turns down, so you can see it better, and then it turns to the left and to the right. It can be in the 8-member ring, 2 aluminum atoms as third neighbors, and the final structure is in 2 adjacent 10-member rings, still as a third neighbor. So we have almost complete confidence that we've got that structure right. But as you can imagine, you cannot expect all the aluminum to be in those special places in the zeolite. There has to be other aluminum in the zeolite. So there has to be sites where there is an aluminum atom and there is no other neighboring aluminum atom that can serve an additional anchoring site so that the molybdenum species anchors and goes. So for an isolated aluminum site, the structure has to involve an OH group, because otherwise we cannot maintain molybdenum in the +6 oxidation state. That OH group, we try to find the best place for it computationally, and it actually wants to go in molybdenum. So our prediction is that this is a structure with 2 terminal oxygen atoms and an OH on the molybdenum site. So we call this one double aluminum sites, and these ones are single aluminum sites. So this is putting them in the same unit cell so that it's easier to illustrate the difference. So this one has 2 aluminum atoms in a special position so that molybdenum anchors on both of them at the same time. This one is just isolated. If these 2 are too far apart, then they become 2 single aluminum sites. So these are the structures that we've identified. Then we did frequency calculations, and we matched the Raman spectrum. So we have our answer. What are those Raman bands from molybdenum oxide on the surface of ZSM5? So the band at 993 is a symmetric stretch. So we have 2 terminal oxygen atoms, and they vibrate. And this one with a symmetric stretch, 2 oxygens increase the molybdenum oxygen distance at the same time. So they do this. The same motion from the structure on the single aluminum sites, this is the band at 975. And then these structures, we also detect the bending motion, so when the 2 oxygen atoms do this. And both of them, this structure and that structure, so this bending mode is very close to both of them, and we observe just a single band at 325. So with this understanding, we should be able to explore the effect of the catalyst preparation parameters. And that's what we did. So we looked at the effect of the molybdenum loading for the same zeolite. The zeolite was silica aluminum ratio of 15, And what we calculate, so this is the molybdenum loading, which we control. So we're keeping the silicon-aluminum ratio constant. So in effect, the most important parameter that has been rarely reported is the number of aluminum sites, so the entering sites.